Welcome back. Here you see some sodium metal. Let's say that I asked you to go get 6.02 times 10 to the 23rd atoms of sodium, 1 mole of sodium, because we need that much for a particular experiment. This type of request is not that uncommon in chemistry. A chemist often needs to know how many atoms, molecules, or ions that they have for a particular experiment. So how on earth would you know if you have 6.02 times 10 to the 23rd atoms? Oh, and by the way, even if you could see the atoms, it would take more than your lifetime to count that high. Well, chemists have devised ways to count atoms. But in order to understand that, we first need to understand the concepts of formula mass and molar mass. Let's start with formula mass. To understand this, we'll start by reviewing what is the fundamental unit of 3 types of substances: an element, an ionic compound, and a molecular compound. Please fill in the blanks in the chart by naming the fundamental unit for all 3 types of substances. Stop the video now. So for an element, the fundamental unit is an atom, or a molecule if you're talking about a polyatomic form like Br2, P4, etc. For an ionic compound, it's a formula unit, and for a molecular compound, a molecule. Now that we reviewed that, we can state that the formula mass is simply the mass of the fundamental unit of a particular substance. For example, let's say we want to calculate the formula mass of barium phosphate. We make the basic setup like this, with a row for each element and a column for a number of atoms, atomic mass, and total mass. Here's the first row done for you. Since there are 3 atoms of barium in the formula, we multiply 3 by the atomic mass of barium, which comes from the periodic table, to get the total mass due to barium, 411.9 AMU. Now please complete the chart, then add the total mass of each element, this column, to get the formula mass for barium phosphate. Stop the video now. So, the formula mass is 601.8 AMUs. Make sure to ask in class if you're not sure how we arrived at that. Now, since barium phosphate is ionic, making the fundamental unit a formula unit, a more precise way to write the units here would be 601.8 AMUs per formula unit. As a side note, the term molecular mass can be used in place of formula mass when referring to molecular compounds. So if you're ever asked to calculate the molecular mass, you do the calculation exactly the same way. The only difference is the units would be AMUs per molecule. Let's now move on to molar mass. Not molecular mass, molar mass. The first thing to emphasize here is you calculate the molar mass exactly the same way you calculate the formula mass or the molecular mass. So you already know how to do it. The only difference is the units are different. The units are no longer AMU because, as the name molar implies, the molar mass is not the mass of the fundamental unit of a substance, but rather the mass of 1 mole of fundamental units, 6.02 times 10 to the 23rd of them. That's a lot of fundamental units. For example, what you see circled here in red is 1 formula unit of sodium chloride. In other words, 1 sodium ion and 1 chloride ion combined to make 1 formula unit. Whatever the mass of those 2 ions is represents the formula mass of sodium chloride. But the molar mass of sodium chloride is the mass of not just one of those units, but 6.02 times 10 to the 23rd of those units. That means you would need to add the mass of that first unit, plus this one, plus this one, plus this one, and so on, until you've added 6.02 times 10 to the 23rd of them. Therefore, the unit of molar mass must be much larger than formula mass. And in fact, it is. The unit of mass for molar mass is a gram, or more precisely, grams per mole. Let's look at this more closely. In the first row of this table, we have our result for barium phosphate that we calculated a minute or so ago. The formula mass was 601.8 AMUs per formula unit. That means 1 tiny little formula unit, which is comprised of 3 very small barium ions and 2 very small phosphate ions, weighs 601.8 AMUs. That's a really small mass. Now let's move to the molar mass column, and we see the molar mass is the same number but different units. The units are now grams per mole. This means that 1 mole of barium phosphate formula units, which is a lot of formula units, 6.02 times 10 to the 23rd to be precise, has a mass of 601.8 grams. In the next row, we see the results for water. The formula mass is 18.02 AMUs per molecule. If you're wondering where the 18.02 came from, you perform a calculation similar to what we did for barium phosphate by finding the atomic masses from the periodic table. If you're wondering why it's per molecule, that's because H2O is molecular. What all this means is one tiny little molecule of H2O, 2 hydrogen atoms and 1 oxygen atom, weighs 18.02 AMUs. It follows then that the molar mass of water is 18.02 grams per mole, which means a mole of water molecules weighs 18.02 grams. And in the last row, we see similar results for zinc. We get the 65.39 from the periodic table. Make sure to ask in class if you're not sure about any of this. By far, the more useful of these two, formula mass or molar mass, is molar mass. This is because it's not practical to deal with such small quantities such as 1 atom or 1 molecule or 1 formula unit, although emerging nanotechnology might be changing this. But it is practical to deal with 1 mole of atoms or 1 mole of molecules or 1 mole of formula units, because that's a quantity we can see and use. If you learn nothing else from this brief lesson, remember that the units of molar mass are grams per mole. And if you're wondering, is it just a coincidence that the number for formula mass, like 65.39 in the case of zinc, and the number for molar mass, which is also 65.39, is the same, but the different units? And the answer is no, it's not just a coincidence. It was made to be that way. Ask in class if you want to know more about that. Okay, let's wrap up with 3 review questions. First, determine the formula mass of ammonium sulfide. Include units in your answer. Stop the video now. We get 68.17 AMUs per formula unit. It's per formula unit because ammonium sulfide is ionic. This is one of those compounds that even though it's all nonmetals, it's still ionic. Whenever you see the ammonium ion, think of it as taking the role of the metal cation. Now please find the molar mass of ammonium sulfide, including the units. Stop the video now. I hope you didn't spend a lot of time on that. It's the same number, 68.17, but now the units are grams per mole. All right, last one. What is the molar mass of sodium? Stop the video now. 22.99 grams per mole. Don't forget the units. The 22.99 is the atomic mass of sodium from the periodic table. A final comment here. Recall that we began this lesson by asking you to get 6.02 times 10 to the 23rd atoms of sodium. At first glance, that seems really problematic. You need to count 6.02 times 10 to the 23rd atoms, and you can't see them. And even if you could, it would take more than your lifetime to count that much. So when a chemist needs to count atoms, they do so indirectly. Take a close look at that 22.99 grams per mole you see here. Stop the video for about 10 seconds and predict how a chemist indirectly counts atoms. Chemists count by weighing. If we weigh out 22.99 grams of sodium, since that is 1 mole of sodium, then we know we have 6.02 times 10 to the 23rd atoms of sodium. Well, thanks for listening, and I'll see you next time.